thank you very much. It's a pleasure to be here, if a bit of a surprise. I think one of the things I'll mention about collaboration, about the Large Hadron Collider project, one of the features I hope you'll get across will be the nature of sustained international collaboration. And I think there's probably no better vindication of that than the fact that Imperial and UCL can actually work together on a talk. So, without further ado, the Large Hadron Collider is, of course, a particle physics project. Particle physics is essentially one of the frontiers of knowledge, one of the frontiers in a centuries-old effort, which is now diversified in several areas, but this is the one that kind of stays focused on looking at the smallest and most fundamental objects and the laws of nature that govern them. And one thing we've seen in this kind of centuries-old quest, if you like, to understand the universe around us, is that over and over again, as we gain understanding, we collect data, we collect more and more data, we gain understanding by looking at the data, and the variety, a huge variety of phenomena periodically yield to some kind of unifying principle. We suddenly go, that's what's going on there. And there are various examples of that. The greatest advances of the past have been some steps towards this. For instance, you can view Isaac Newton's work in the 17th century as basically proving that gravity, that celestial mechanics, was actually run by the same thing that made apples apocryphally fall out of trees. And also in the 19th century, Maxwell's work on electricity and magnetism that Faraday had been investigating experimentally, the Maxwell's equations somehow made all this kind of obvious, that this is some same phenomena going on, different manifestations of the same underlying principles. And again, in the 20th century, Einstein basically unified space and time in some sense, and showed that as you travel fast, you essentially mix these things up in a way that makes them different manifestations of the same kind of geometry. And again, chemistry and atomic physics, quantum mechanics kind of brings that together and explains the periodic table in terms of the quantum mechanics of atoms. So that's some kind of physicist view of what was going on, some snippets of history from this, for instance, and how that relates to innovation. You can say, for instance, J.J. Thomson discovering the electron. About 50 years later, you get the first semiconductor transistors, and we end up with a world that revolves around electronics to a very large extent. Similarly, Einstein's insight thing he got his Nobel Prize for was that photons, packets of energy, are the best way of explaining what's going on in the photoelectric effect. We start understanding how this can be made coherent, the laws of lasing. The first lasers were made basically as a solution looking for a problem to solve, and now high bandwidth communications and a multitude of other applications, including the recent Nobel Prize for transmission through optical fibres, are benefiting from that. So what we see over and again, and there's no reason to think this virtuous circle has stopped, is that advances in fundamental science drive advances in technologies and alter the way we live, and they also enable the next advances in science, as I think you'll see in this talk. So that's a kind of historical point of view. Where does the LHC fit in on all of this? Well, one of the great achievements of the 20th century science is the Standard Model of particle physics, which essentially puts together relativistic quantum theories of three of the four fundamental forces. Gravity is left out, and that's one of the things that we have a slim chance of addressing maybe at the Large Hadron Collider. It's certainly one of the big outstanding problems, but the fact that we've got three of them in this kind of unified quantum mechanical picture, this mathematical formalism, is a major achievement. It's a very few parameters to describe a huge array of phenomena. And what we see is these three forces are very, very different, but it looks in the Standard Model as though the differences between them are due to the fact of kind of condensed out from. So if you look back at the Big Bang, when the whole of the universe was crammed into a much smaller space, same amount of energy in a much smaller space, it looks like these forces had a lot more in common. They look much more similar than they do now. And as the universe cooled, they've the symmetries between them have been broken. And so you see the kind of graphical representation of this, along with some data from my previous experiment before the LHC, where up here, these are two scattering processes, one where you're involving the weak interaction, which is the red line here, one involving the electromagnetic interaction, and this axis here is essentially the number of events, the number of times something happens. And along here, you've got the energy. And you see that at very high energies, these weak and the electromagnetic force are essentially the same strength. In some sense, they're unified. And as you condense down to everyday energies down here, they're very, very different. This is a log scale. There's orders of magnitude difference between them. And this is, of course, why we have electric lights look very different from the weak nuclear force which drives the sun at our energies. But in some sense, above this, what we call the electroweak symmetry breaking scale, they were unified. Now we think that we understand why this symmetry is broken. It's basically because the mass of the W and the Z, which carry the weak force, is much bigger than the mass of the photon, which carries the electromagnetic force. But that kind of just begs the question, so why is the mass different then? And that's the key to the Large Hadron Collider. The mass, as far as we know, is different due to some, well, we know it's due to some missing element in our theory. In the standard model, that missing element is actually the Higgs boson, and it's needed to make the whole theory work, but we've no evidence for it other than the fact that the theory works. So that's why so you hear the LHC is looking for the Higgs boson. I don't really like that phraseology, looking for the Higgs boson. It sounds like we want the last stamp in our album. What we're really doing is doing physics for the first time above the electroweak symmetry breaking scale. So whatever it is that breaks this symmetry between these forces, we will look at it, we will understand it, we'll more about it from the Large Hadron Collider. If it's a Higgs boson, we'll find it. If we don't find a Higgs boson, something else has to be doing something there, because we know there's new physics there. This is data, we know those lines come together. In our theory, it's the Higgs that makes them separate at low energies. But if it's not the Higgs, we will find out what's going on. So that's why the LHC is worth the effort, and you'll see it's a lot of effort. Another reason, a more speculative reason, but still very exciting for what that we might find at the Large Hadron Collider, is from cosmology. There are big connections between particle physics and cosmology. And in cosmology, dark matter and dark energy are needed in order to make our picture of the universe work, and we don't know what either of them are. I'm not convinced at all that we'll find anything about dark energy at the Large Hadron Collider, but certainly there's a very good chance that we'll produce dark matter candidates in the lab for the first time. Okay. So particle physics, as I said, it's the modern name for this centuries-old effort to understand the laws of nature. And basically what we're doing is trying to find out what are the elementary constituents of matter and what are the forces that control their behaviour. Experimentally, to do that, what we tend to do is get particles to interact and study the resulting products and features. We measure the energy, direction, the identity, and identify the products as precise as we can, and we deduce from that what was the physics. And in order to do that, we use accelerators. So particle accelerators, they accelerate particles to high energies, as the name would suggest. The higher energies, why do we need higher energies? Well, there are several ways of phrasing what is almost the same reason, but they're not quite the same thing. One is that to look at short distances, you have a resolution parameter. The energy goes like 1 over the size. So if you want to look at very small sizes, you need very high energies. They're basically powerful microscopes from that point of view. We want to create and discover new particles, and therefore, if their particles are heavy, then we need a lot of energy because of E equals mc squared, c being a big number. And also, they allow us to probe the conditions of the early universe. And again, that's when the ambient temperature, the equilibrium in the universe, every particle at some point had the energy that the two protons colliding at the Large Hadron Collider had at some point in the early universe. And this is basically Boltzmann gives you the key that to get to those high temperatures, we need those high energies. So we're revisiting the early moments of the universe, in this and that also, in a sense, tells us things about how the large-scale structure of the universe it was formed, and that's, in some sense, they're powerful telescopes in that sense as well. What we're doing is observing phenomena and particles normally no longer visible in everyday experience, but it's important to note this is not a historical study. It is telling us physics that was very important in the first few moments, but these are the fundamental physical laws that drive the current universe as well. And we're doing it all in a controlled way in the lab.